All right. Now, before we talk about the consequences of these, let's take a step back and think about what we just talked about. So we just talked about assumptions underlying ordinary least squares, this one way of doing estimation. And here they all are. And hopefully you understand them at least in some fashion. But here's the thing I want you to note is that all of these assumptions are assumptions about population parameters. So each of these have Greek letters in them. So linearity says something about these betas. Well, these betas are the true coefficients, or the true population effect of of wage on income. And no indigeneity says that these errors are uncorrelated with the axis. But these errors, again, Greek symbol, these are population quantities. We can't observe these things. Normality and homoskedasticity also are assumptions about this unobservable population quantity called epsilon, or error. No autocorrelation, again, says something about how these epsilons are related to one another. No multicollinearity, actually, that one we can test for. So that one's straightforward. The rest of these are statements about population quantities. Now, remember, from last term, and from this term, we can never observe population quantities. There is some true effect of education on wage. It's called beta 1. It lives in the population. I'll never know what it is. I can estimate it. I can do inference. We can test hypotheses about that thing. But this number, beta 1, I'll never be able to see. Likewise, these errors, I can't observe them. Why? Because they are population quantities. So all of these assumptions are about things that we can't ever see or observe or know. So at this point, you might be thinking, Moser, you're mad.
This puffin got some stuffing for your puffin muffin.
How on earth can we do something like this? And as you'll see in lab, the answer is kind of deceptively simple. It's rather clever. In a nutshell, the idea is, okay, yeah, that's true. These are all population quantities, and we can't see them. But you know, in the past, we haven't been too bogged down by the by the impossibility of this task. Why? Because we just turned to estimation. We just said, all right, fine. I can't ever know truly what beta 1 is, but I can estimate it, and I can do hypothesis testing, and I can calculate a confidence interval, and I can say how unsure am I of this here estimate, and so on and so forth. And that's the similar idea. So for example, all of these assumptions about these errors that are important, namely normality and homoskedasticity, which remember is really 3 in 1, autocorrelation business, all of these are assumptions about errors. Again, errors are these idiosyncratic terms that can never be observed in the populations. That it's all the stuff that's unique to me, that's unique to my wage that isn't my education. How on earth are we could we observe that, or could we estimate that? The answer is, well, we can't observe that, but believe it or not, we can estimate it. How?
Oh, hon, I meant to tell you, last night at Pete's, I rolled a full house, right?
Oh.
And I decided to go for it,
Right.
and I got a Yahtzee.
That's so brave, hon. I always keep the odd numbers. They feel so cozy.
Oh, hold on.
Let me show you quickly from seminar. So conceptually now, suppose this here blue line is our regression line. So we've done regression, chug, 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 and R is spit out. It's estimated beta naught and give us a number B naught, and it's estimated the slope. Let's call that B1. And so we've estimated this here blue line. This here blue line represents our estimation, the regression line. So remember, estimation results in a way of making predictions. So for any value of x, if I were to say, hey, if x were 200, what's your best guess for y? Well, this here blue line gives you a way of answering that question. How? By saying, okay, if x is 200, then this here line, y would be, 16 or 17, let's say. So for any value of x, this here regression line, this here blue line, gives us a way of making predictions, coming up with these y hats. But look, we've observed some observations with an x of 100 or let's say 90. So here's an observation. Here's something we actually saw, and it had a value of 90. And so we can ask, what is our best guess? What is our prediction of y if x is a value of 90? Well, this here blue line gives us a way of doing that, and the answer is, let's say that's 12. So that's a prediction, 12. We've guessed 12 when x is 90. But we can compare that to what we actually observed. Really, what we saw a value when x is 90, and it's this here black dot. And when x is 90, we observed that y was 11. So we were some amount wrong. And the wrongness of our prediction, conceptually, is just the distance, is the vertical distance between this here black dot and this here blue line. So it's just this red, the horizontal red bit. If you remember, ordinary least squares was chosen to minimize the sum of these essentially to make these red bars as short as possible. So that's how we've come up with this here blue line. And of course, there's still some prediction error, which is these red lines. But now hang on. Here's the clever bit, which I did not come up with at all hundreds of years ago. This here red line could, in a sense, be viewed as an estimate of this person's error term. Why? Because this here red line represents everything that went into this here person's value of y that isn't x. This here person has a value of x of 310 and a value of y of 13. Using only what we know about x, we could predict this here person's value of y. So if you like this, the blue line represents our estimate of that systematic component, the first part of the population equation. So what else goes into determining this here person's value of y? Well, by assumption, it's x, and it's everything that isn't x. Well, everything that isn't x is just this here red line. It's just the difference between the bit that is x and what the final value, the actual value of y. Well, that's just this here red line. And so, believe it or not, this red line is called the residual or residual error, can be used as an estimate for this person's realized error. And doing so in the seminar, you'll see that's one way that we can start doing diagnostics. That's one way we can start asking, well, is there reason to think that these are satisfied? Or is there reason to think that these are violated? How can we check? And that's the preview. That's the idea. Okay, so now consequences. What if these magical population quantity assumptions hold? And the answer is, if these assumptions hold, then ordinary least squares is a really good way to do estimation. Actually, it's better than that. It's the best way to do estimation in a sense we can make precise, well, in a sense that Gauss and Markov made precise. So the so-called Gauss-Markov theorem tells us that if these assumptions are satisfied, the ones that we just talked about, then ordinary least squares, abbreviated OLS, is as good as it gets in the following sense. It is the best linear unbiased, it is the best linear unbiased estimator. Okay, so what does that mean? Well, we know what estimator means. An estimator is a way of coming up with guesses based on observed data. Unbiased, what does unbiased mean? Unbiased, we know what unbiased means. It means that this way of coming up with guesses might not be right every time. It won't always accurately estimate beta 1 or beta naught, but we know that on average it will. If we use ordinary least squares over and over and over and over again under repeated sampling, that on average, all of those guesses will be exactly right. That's what unbiased means. So that's nice. Linear, well, linear just means that among the class of all estimators that are linear, so this is kind of technical, that ordinary least squares is best. So what does best mean in this sense? So best here means the most precise. Ordinary least squares is an estimator. It's a way of coming up with guesses. Each of those guesses, we have some amount of uncertainty among. And what the result of Gauss-Markov says is that the uncertainty associated with ordinary least squares guesses is as small as they can possibly be. If you were to use any other way of coming up with an estimate, coming up with guesses, they would be less precise. You would be more unsure of those estimates than you would be if you used ordinary least squares to estimate those betas. And you can kind of, well, I don't know if you can see it or not, but it comes from how ordinary least squares works. Ordinary least squares is built to do this, right? It minimizes the sum of the squared errors. It comes up with its guesses in a way so as to make those errors as small as possible. They can't be zero because there's noise in the world. There are factors causing income that aren't education, that we haven't included, that are in that error term. Okay. Consequences. So what happens if we so let's just quickly review the assumptions. So linearity, we've said that the regression model is linear in the parameters, not necessarily in those x's, as we saw. Random sampling, the data come from, again, this is one of these maintained assumptions. We're always assuming that what we observe, the sample is determined in some part at random, and we need to go a little stronger here and assume that these observations are independent. Another way to think about that is me being in the sample doesn't affect the probability of you being in the sample. So that might be violated if you were sampling like couples. If you sampled a husband and you're observing couples, then you've automatically included his spouse. Zero conditional mean, the expected value of the error term is 0. This is trivial, this is fine. No perfect collinearity, so we haven't double counted. This is also kind of technical, so we can't have both income as measured in pounds and income as measured in pence. Okay, great. Homoskedasticity, funny word, fun to say. The error term has constant variance, so those errors are not the same for everybody, but equally random, but come from the same distribution. And indeed, that distribution is a normal one. What happens if these don't hold? So I won't belabor it because here's a little slide that tells you the assumption, what can go wrong? The worst thing that can go wrong is indigeneity. If you have indigeneity, then we've lost even unbiasedness. So we can't even estimate those coefficients very well. So this is why indigeneity is a real problem. And you can kind of see why indigeneity is a problem, because if the errors are correlated with the x's, then that means you're running the risk of having spurious or confounding relationships. Something could be causing x and y that we haven't included, and so we have no prayer of estimating the independent effect of x on y. So that's the most serious. The second most serious would be normality. If the errors aren't normally distributed, then estimation we can still do. We still have unbiased estimates. The issue is hypothesis testing is hard. The uncertainty in those estimates gets trickier. There are ways around this. It's not the end of the world, but it's probably second worst. The least offensive or violation is that the residuals is the assumption of constant variance. So if those errors are differently varied, that's really not a big deal. Our estimates using ordinary least squares are still unbiased. They're still pretty good. It's just they're not best in the sense of we could come up with a weighted ordinary least squares estimator that does a little bit better in terms of efficiency. But that's not a huge. This isn't a huge. Violating the constant variance of the residuals is not a huge deal. Okay, and what's up next? Well, we've seen some of this already. Hypothesis testing. So we've got estimates. Estimates are guesses. Like anything, we could test the hypothesis that the effect of wage the effect of education on income, that beta 1, we could test the hypothesis that number is 0. And what would that mean substantively? That would mean substantively that there is no effect of education on income. So we can do that. And next week, what we'll do is we'll look at we have estimates, we have a fitted model, we have a regression model. How good is this model? And as we'll see, there's sort of two subtly different ways of even answering this question that that both give rise to interesting features and properties. So how good is a model? Well, one way to answer that is to ask, how well are our predictions? Remember, once we have an estimate, once we have a line, we have a way of making predictions. And we can ask, how good are those predictions? There's another, it turns out to be more useful or more interesting for social science research, way to answer the question, how good a job did we do? How good is the model? And that is by asking how much observed variation in Y can be accounted for by X. And this will give rise to the formalism needed to answer the question we began this part of the module with, and that is, what does it mean to say one variable explains another? We can cash that out in using this second approach to model checking, basically. That is to say, how much variance, how much variability in Y does X account for? And we'll make that precise next week. Bye!
Yeah. Oh, that reminds me. I need socks and I need bin liners.